Hi, my name is AJ Bonkin, and this is Gophers Writing Elephants, writing Postgres tools in Go. And before we get started, thank you guys all for coming, and thank the PGConf committee for having me talk. So really quick, who am I? I'm a senior site reliability engineer at Procore. I focus on availability, performance, and security, and I've been writing Go code actively for about 2 years. So really quick, who is this talk for? So this is a talk really focused on tool creators and people who would be creating tools. So, database engineers, DBAs, operations folks. Go is a great language for writing applications, and there are some great ORMs in Go. I'm just not really going to be talking about this. This is really focused in the context of creating tools for interacting with Postgres. Okay, so really quick, let's go do an overview of Go. That is not working, okay. Go is an open source programming language that makes it easy to build, that was built with the idea of making it easy to build simple, reliable, and efficient software. Go was created by Google, and it was built for Google as well, right? So a big focus on things like reliability, being good for teams, and being good for building the kinds of things they need to build. So in the standard library, there's some truly world-class networking and cryptography libraries, among other things. And there's this super important article in the context of Go titled "Less is Exceptionally More" by Rob Pike, who is one of the original creators of Go. And the main idea there is that they stripped a lot of features from kind of typical language features in creating Go. Another creator of the Go programming language is Ken Thompson, who is co-creator of C and of Unix. And they cut a lot of these language features, and Go is purposely lacking these, and and he argues that there's an extreme amount of benefit for that, though it is very strange for people coming from really any language, because there's, my favorite language feature X that isn't in Go. But he argues that this is a very good thing, because it makes this intense focus on simplicity and explicitness, and there being kind of like the one true way to do this thing in Go, and which makes it very good for teams, and all of that encompassing makes it a very reliable programming language. And of course, it's statically typed, compiled, and garbage collected. And this is what it looks like: a hello world, world being in Mandarin characters, and Unicode support by default. So why Go with Postgres, right? So at Procore, we're a Ruby on Rails shop, and we have a bunch of Ruby scripts as well as some Bash scripts for interacting with Postgres, and those are awesome. Scripting languages are great for writing scripts, but whenever I need something a little more, and usually when I'm trying to create a more full-featured tool, I want to argue about it, there's a lot of benefit in moving to something like Go. And as well, if you're using C or C++, that there's some benefit. You get to retain some of the awesomeness of using those languages and gain a lot as well, whether it be scripting languages or C and C++. And so there's three main reasons. So the first one is performance. And so this is something that I would say you would retain from using C or C++ and gain from any of the scripting languages. So Go is pretty fast. This is a kind of a contrite example, but it was probably the prettiest visualization I could find. And it's a benchmark of a very simple JSON over HTTP API with measuring the requests per second. And so for Go, it's 21,000 requests per second. Next one down being Node, and then below that, Vapor at 10,000 requests per second, which is Swift on the back end. The garbage collector is awesome. And so this, of course, doesn't really matter if you're not dealing with a lot of data. But in one of my examples, and I think commonly in working with Postgres, you are dealing with a lot of data. And so the last 2.5 years, the Go core team has been focusing extensively on the garbage collector, making it extremely fast. Concurrency is a breeze. So this is where you get into some of the exciting pieces of Go, right? So you've got this function say that takes a string, loops 5 times, sleeps for 100 milliseconds, and then prints the string passed in. And in the main function, we prepend the execution of that function with the word go, the highlighted piece. And what that does is that launches that function execution into a Go routine, which you can think of as an extremely, extremely lightweight thread. It's not a thread, but it's very similar in a lot of ways. And makes it concurrent and potentially parallel, right? So if you're running 4 Go routines and you have 4 cores and they're purely CPU-bound operations, then it's going to run them in parallel. But depending on, it can do a lot of the parallelism for CPU operations, for network files, whatever it be. And so, yeah, it's extremely easy. And so you get that staggered execution from running something like that. So the number 2 thing is reliability. And this is something I would argue you gain a lot, whether you be coming from C or C++ or any of the scripting languages. The statically typed, very simple type system. It's a very simple programming language. And so this kind of brings a lot of pieces of Go at you at one point, but I think it's an important example for showing the the explicitness and simplicity and how that is a very good thing. So at the top, you've got this type event processor struct, which is a struct just like in C, and it has one thing in it, which is an event queue, which is a channel that takes events. And a chan or channel, you can think of it pretty much like a first in, first out queue. And the first method on it, add, takes an event, puts it onto the queue. The second method, start, is an infinite for loop that pops an event off of the event queue and then runs its process method in a Go routine. And so of course this is cutting a lot out from what you would need for this to work, but it shows how if you need something like a background event processing functionality within your tool, like it's not that many lines of code and it's extremely easy to just put in there. Testing is simple and built in. So it's built in meaning it ships with the standard library. And Go test looks for any files that are, whatever _ test.go. So like the middle processing _ test.go, and runs your tests and has some really cool features like this built-in race detector where you don't need to change your tests at all, just -- race at the end, and it runs this race detector throughout the execution of your test, looking for things like concurrent writes, concurrent write read, etc., and will warn you if it detects any race conditions. So error handling. So Go doesn't have exceptions, but instead has errors. And the idea here is that any function that can have any sort of error will return an error as the last parameter. And so at the top, myfunct takes no parameters and returns a string and an error. And then the first line within that is kind of what that would look like to execute, where you execute this function run and it returns a string and an error. And so you check if error does not equal nil, meaning that an error was returned, then return empty string or whatever and an error. Else return, my string and nil. And so you get a bunch of this, if error doesn't equal nil checking in Go code. But what it means is that every error that can occur, you are able to make a decision very explicitly about what to do in that. And so of course you can just ignore all these errors, but in quote unquote production Go code, you see explicit handling of these errors. Should I panic out and just quit? For example, like if I'm starting up and I'm trying to connect to the database, if I can't connect, I should just panic. Or should I, log an error, or just log a warning and continue on, et cetera. You get this explicit handling of what I should do in the case of an error at this function execution. And a common one, and kind of the simplest form, is this bottom example, must myfunct. And so you'll see the prepend of the word must in front of a function if it shouldn't return error and instead should just panic. And so if error does not equal nil, just panic. And so the third and last one is ease of use. And this is something I would say you really retain from like a scripting language and can gain extensively from C or C++. So tooling, right? So the first one, GoFMT or GoFumpt, is a built-in code style formatter that works perfectly as long as your syntax is right, and shipped, I think, with 1.0 of Go, I'm not sure, but from very, very early on in the standard shipping of Go. And even though I personally, and probably some of you here, don't necessarily agree with what its style is, I truly feel that consistent style throughout a project, for example, is significantly better than mixed styles. And so, for example, I prefer spaces on everything I do over tabs, right? But Go says we use tabs. And so GoFumpt, when you run it, it just replaces spaces with tabs. And there's some really cool pieces of that. So it's very common for on save to have your editor just run gofumpt on the file. And so my editor, which is Vim in this case, I have like nothing configured around tabs, but I just write my Go code using spaces, and then I save it, and it will just run gofumpt and replace it with tabs. And so testing, right? I mentioned testing. Testing is good and awesome. Godocs. So Godocs is very similar to Sphinx, if you're familiar, where it basically is parsing the comments and creating a very usable HTML document for reading the documentations. And there's also godocs.org, which will just pull in any sort of open source library, usually from like GitHub. Go build is for building your binaries, and it's super easy to do cross-compilation for different platforms and architectures. And then Go run basically builds into temp and then runs it from there. And it's super, like compilation is super, super fast, and it feels like I'm using an interpreted language. And then lastly, I put in Vim Go because I'm a Vim user, but really, I just wanted to mention that there's like truly full-featured support for Go in editors and IDEs and CI tools and application monitoring tools and any of these kind of like third-party developer tools. Familiarity, right? Go is an extremely familiar language, taken a lot from C and then pieces from like Python and JavaScript, and then as with any new language, some pieces from some more esoteric languages. The library support is awesome nowadays. This wasn't true when I was first getting started, but now it's incredible. Tons of small, medium, big companies using Go and creating libraries and open sourcing them. And it's extremely easy to install. So in your typical like open source library hosted on GitHub, you're running Go space git, github.com / the owner / the repo name. So distributed single binary anywhere. So in this case, this is for a project called dbduke, which I'll be talking about in a little bit. And I run Go build. And so this is on my MacBook Pro. So I'm going to get a binary for OSX 64-bit. If I prepend this environment variable, or just set this environment variable GoOS to Linux, I'm going to get an ELF 64-bit. If I also include this Go Arch one, then I can get an ELF 32-bit executable. And as you'll notice here, right, both of these are statically linked. So in Procore's case, all of our servers run, almost all of our servers, run 64-bit Linux. So if I'm working on some project, I just run this, and then I've got a binary that I can just SCP up and use. And of course, when you're like shipping it out, you want to use package managers and all that stuff, but it's extremely easy to build. It's also extremely easy to build this in, say, like CI or whatever it may be. So there you go, right? Performance, reliability, and ease of use. And I want to, in a minute, dive into some examples to further illustrate what I mean exactly with these, within specific use cases. But performance, something that I think you really retain from C or C++ and gain from scripting languages. Reliability, something you're definitely gaining, in my opinion, from both of those. And ease of use, something you're retaining from your scripting languages and gaining from something like C or C++. So quick little sidetrack. Interacting with Postgres and Go. So in this standard library, there is this database /SQL, which basically provides like a core API for interacting with SQL databases. And so it has things like open and close, begin, rollback, commit for transactions, exec, query, query row for executing queries, and pinging for pinging the database, and then has things like built-in connection pooling. And so with it, you use a driver, which actually implements this for a specific database. So this is my favorite Postgres driver, and you use it a little something like this, where you're doing your imports, and then here you've got your connection parameters, and here's the main thing that will get your DB object, where SQL.open, the name of the driver, and then your connection parameters, and this will return a DB object. So if error is equal to nil, then we continue on, and we call db.queryRow select one. This returns a row object. And from there, we can call its method .scan, pass in the variable that we want to put the result into. So in this case, it's just a simple int, but it can be a struct with many fields in it. And that scan method also returns an error. So if error is equal to nil, we're done and we've got our result. So, okay, now the real world examples. So PGNet Detective. PGNet Detective is currently open source. and go to github.com/procore/pgnetdetective and check it out. But before I explain what exactly it is, I want to tell a little story. So the beginning of this year, my boss posted this picture into our Slack channel. We were using Ganglia and Graphite at the time. I was like, what is going on? And so what this is, I wonder how good, easy to see. Okay, that's pretty well. What this is this is a network, the network traffic on our main production database. And this blue line is bytes out. And the y-axis is bytes per second, with the bottom being 0 and the top being 128 megabytes per second, or the top being pretty much like 1 gigabit. And so you can see this spike going up to about 105 megabytes a second. We're like, what is going on? So we started looking around Ganglia and Graphite, and we come across this graph, this crazy rainbow graph. And what this is this is aggregate bytes in to our utility servers, which are basically like our background worker servers. And so at the time there was 27, and there's a spike up to about like 70 megabytes per second going into them at 2 different points. And it's evenly distributed between like 6 to 10 of these servers throughout the periods. So there's no like single bad actor in this, right? It's like, okay, what is going on? And we look in the slow query log, turn on full logging, like trying to just see what's going on. And we can't really find anything that would seem obvious to be causing this. Like, okay, so we go onto one of those background worker servers and take a network capture, because that's really what we're trying to find. And we open it up in Wireshark and just not really seeing anything weird. Like, no packets that seem, there's no like sequence of similar packets that are much more than any of the other ones, like nothing strange. It's like, okay, what we really want to do is take a network capture on the main production database and do pretty much 2 things. First is like normalize all the queries and get them together, and then get all of their response packets that are going out of the database server and correlate them to those queries, so we can find like what query is causing an exorbitant amount of data going out of the database server. And so I take a little network capture on the main database server and build this little prototype using Scapy, which, if you're not familiar, is a Python library for working with packets. Has an awesome interactive shell. And so start working with those and seeing if we can do this. And I'm hitting this problem where, like, with a super small capture, it's extremely slow, like really, really slow, because there's a lot of looping that needs to occur in, like, getting all of these and then correlating them together and all of that. And so, like, and to even make that worse, like when you run a fairly simple TCP dump for like any interface, port 5432 on our main production database, it's about 1 gigabyte every 10 seconds. So trying to get a sizable capture of maybe like 2 minutes is a 12 gigabyte file. So I'm working with like a sub 50 megabyte file, and it's slow. So okay, like we need something faster. Let me build the real version in Go. And so the first piece that I need is something to interface with these capture files and work with these packets in Go, because everything else in PGNet Detective is pretty much like general purpose programming stuff, but there's this piece. And so I find this awesome library, Go Packet, provides packet processing capabilities for Go. And what it lets me do is kind of like loop through these packets and say at the top, right, if this TCP packet's destination port is 5432, meaning it's coming into the database server, and it's prefixed with a capital P, which in the Postgres wire protocol is a parse packet, which will contain a query, then okay, normalize the query, increment the counter, and collect some of its metadata. Else, if the source port is 5432 and it's an ACK, meaning it's leaving the database server, append it as a response, save some metadata, and save the size of the TCP packet. So this way I can start to correlate these between. So I run this, and I get some output like this. This is very strange. There's a catalog query. And you'll notice at the bottom, right, total query packets to total response packets was like a 1 to 1,000 ratio. Okay, what is going on here? And how is this causing problems? And so to rewind a little bit, I mentioned at the beginning that we're a Ruby on Rails shop. And Ruby on Rails, its main ORM is active record. And something important about active record is that it doesn't store the schema in code, but rather when you boot up a process, every time it needs to work with a model, it queries the database to get the schema information and then caches that and uses it for the life of the process. And so in almost all cases, this is never a problem. It's an extremely fast operation and it only needs to do it once for every model it interfaces with. So it's usually not a problem. The problem is, at the time, we were using something called Resque. Resque was created by GitHub, and it is, for the most part, a pretty good thing, but it's for running jobs in the background. So it was what was running on these background worker servers. The problem with Resque is that it forks itself for every job that it runs. So when it forks the process, it doesn't retain the cache of the schema information that Active Record has collected. So every time it runs a job, it forks itself, and every model that job interacts with, it needs to query the database for the schema information. And so when you start running, tens of thousands of jobs per hour, maybe up to 8 tables being touched per job, maybe around 20 columns per table, that starts to become a lot of data going through the pipes. And so during spikes, we were seeing this hit almost the 1 gigabit limit. And so for that and many other reasons, we're switching to something called Sidekick, which is very similar except for it's threaded, so it's able to retain that schema cache. So in this case, where did Go win with PGNet Detective and needing to build this? So performance. So like out of the box, before any sort of optimization, Go was extremely faster. And from going, I wish I had better numbers and benchmarking them, but I didn't truly build out the Python one. I ditched it super fast in realizing how slow it was going to be. And Go out of the box was extremely performant, and then making it use the garbage collector a little bit more, it was very, very fast. And the community, right? Okay, so I need this library to interface with packets. Oh, here's a super awesome world-class library created by Google and used by Google in production. There you go, the best case that there could have been. And again, it's open source. Please check it out and bug me on Twitter or email me if it doesn't work for you, and I'll help you out. So example number 2, dbduke. So dbduke is not open source, and it won't be. It's extremely specific to Procore and Procore's needs. At the end of this talk, or at any point after, if you're at all interested in seeing code snippets or want to learn more about it, please feel free to reach out to me. It's not necessarily proprietary, it's just very, very Procore specific, so I'm not going to be open sourcing it. So to set a little context, we restore staging, QA, testing databases frequently, maybe around 30 times a week. And it's super important that they restore successfully. Because when they don't, productivity dies. Productivity dies for the developers deving based off of them or the QAs testing stuff based off of them. And this problem too is where restores would sometimes fail from super easily recoverable errors. And then the process of kicking them off by hand was very faulty. And what it would mean is one of us would SSH into this machine, start a tmux, run the script, and then just let it sit there. And that kind of sucks. And so what dbduke is a tool for making restores of Postgres databases manageable and fault tolerant. So to first go into the manageability piece here, right? Run dbduke as a daemon with jobs. And so this is something that is super simple. There's nothing in this that is cutting edge by any means. But the point that I want to start to make with dbduke is that so there's these different pieces that I wanted to do, and it was extremely easy and extremely fast for me to bust out a prototype. I'm talking a couple hours after dinner at night, very, very fast to start getting this working. And the idea here is just run these things as a Go routine and then use channels to communicate back to the main process. Very easy, very little code, very explicit what's going on. And then talking about the fault tolerance piece, the idea here is treating restores as a state machine and recovering from failure states. And so this can get as complex as you want it to be, but in the simple case, I started out with this state diagram of, say a staging database is in use, and then it's ready to restore, then it's restoring, then it's ready for use, then it goes back to being in use. And there's this failure state of failed to restore, and we want to bring it back to restoring in that case. And so when I started getting out the skeleton and handling the errors explicitly in the state transfers and the things that occur within that state, which is something that I get from just using Go, the way Go wants me to write it, I started getting the skeleton for a very reliable piece of software in making sure that the database goes through these states. And also with the skeleton in place, as new problems and hopefully new solutions to those problems come up in, say, transferring from one state to another, I have a place to just like, I want to put that code right there. And it's very easy to do. And so, right, so to take a step back and like, what does this error handling kind of look like in Go code? The first two are very simple ones of like erroring out and logging a warning, and then getting into a little bit different one. So, right, so as mentioned earlier, SQL.open, if I get an error back, log fatal F. And so this is using a logging library, and all this is really doing is just printing a log statement and then panicking. Logging a warning. So, right, so drop schema if exists migration cascade. So if this doesn't execute, or returns an error, like that's totally fine. Just log a warning, we'll look at it at some point, but just continue on with what you're doing because the database still absolutely can be used. And then retry with a timeout. So one suggestion I have is if you're doing retry logic, and especially around databases, please, I would suggest use a timeout. I have destroyed databases from not using a timeout. And in this case, without a backoff. So there's some great exponential backoff libraries in Go where you can easily write your own. So the code here is really, really simple. It's more of just a skeleton that I want to talk about, which is, so in this is block till not in use. So blocking that and getting out of that state. So if state is equal to in use, log a warning, go into this for loop, sleep for 15 seconds, quit if the timeout's exceeded, get the current state. If it's no longer in use, then break out, else go back to the top. And so, right, so what I'm trying to get here is not like that any piece of DBDuke is at all cutting edge or crazy. It's just that when I start writing Go code the way Go wants me to write it, I start getting these pieces for free. And not only for free, but with this benefit of it being very easy. And so, right, and so the error handling, as any function that could potentially return an error, I get that, and I get to decide explicitly how I want to handle that error. And then in this case, concurrency was definitely increases performance, but also is very beneficial for ease of use. It was very easy for me to do these kinds of things that I wanted to do. And so, right, so in conclusion, right, Go is not like this one true language that's going to solve all your problems. But in this context of tool building, Go is you get this reliability, performance, and ease of use. And it's been an extreme joy to write in Go and to build these tools in the Go programming language. And so whether you're using scripting languages or like C and C++, you get a lot of these benefits just for free. And of course, there is a high, high cost for language switches, but it's something I would definitely suggest you check out. And as well, at the end of these slides, which I probably won't go to, there's I have some links for looking further into Go and also for interacting with any SQL database in Go. So I'll definitely post these on engineering.procore.com, and I imagine on the PGConf side as well. So yeah, and so the last thing is, if you've liked what I've talked about, and you want to work at a super cool, fast-growing company, and you want to work at a place that looks like these pictures, Procore is hiring. Thanks, guys. Is there any questions? 25 minutes left.
We do know what to use.
Yeah. You guys got some data?
Well, it'd be nice to see some more code. Do you have any of this up in a text editor?
Sure. Let's go with, actually, I don't know. Let's see. Is there anything specifically that you'd want to see?
No, I just want to see some examples. I want to build that up.
Yeah, here, let me see if I can. Let's see, where. Here, this is probably. So for looking at, say, the example of Go packets, yeah. So this is, what is this doing exactly? Oh, it's accepting a PCAP handler, which was read in from in the main function, and lazy loading it in, and then just looping through until Where is it? Ah, so, and then lazy loading it in using next packet until it gets in EOF and then breaking out. And so one of the things, right, is it's getting the IP layer, and then from the IP layer, getting the TCP layer, and then running that checks to kind of extract the specific packets that are important, and then ditching the rest. Which is another piece with Python is Scapy, though like a super, super awesome tool, like loads the entire PCAP file into memory, which if you have like less than 12 gigs of memory and a 12 gigabit capture file, has problems.
So I'm curious, you were mentioning before, or sorry, go ahead. Because did you also talk about parsing the WIFE protocol in addition to what you're doing here, or are you just basically doing this prefix matching and then, like, basically, are you, like, do you have any library for parsing the WIFE protocol itself?
So no, not necessarily. All I'm doing here is extracting the parse packets, and then from there, actually, if you're at all familiar with PG Shark, so I took a lot of stuff from PG Shark and then some other stuff to, and I think that's in utils, to normalize the query from the actual packet itself. And so, yeah.
Did you play around with any other non-libpq database drivers? Like there's jackpq, or jackcpq. There's a couple of other Postgres drivers kicking around.
Mm-hmm.
The reason I'm asking is, did you use PG Bouncer at all in your environment, and or have you had any problems with it in the Go library?
That's a good question. So I actually have never interacted with like through PG Bouncer in Go. Partially that's because Go, it's in standard library database /SQL has built-in connection pooling and uses that through it. So I haven't seen much like use of it. So no.
So you mentioned something about the retry logic. One of the things I've been running into lately at work is we have, a transaction that starts and then a few statements. And because we're serializable, we'll frequently need to sort of go back and back up to the top and restart.
Mm-hmm.
Well, not frequently, but we need to handle that condition in a sort of general way. Is there like a Go way to approach this? I'm really new to Go, so.
Totally. So what is kind of the signal that occurs in the middle of that transaction that says, hey, we should retry this? That it didn't commit?
It's an error with serialization that talks about serialization.
Right. So it depends. So there's kind of, without knowing too much, if we just.
Well, it's very general.
Right. So in Go, say you were getting, I don't know, let's say, so in that classic sense of like, you're getting your query and you're getting, say, row or rows back and an error. If you're doing, like if error doesn't equal nil, then my block. So in here, you could say, like, look for that specific error, and if it's that error, then go back and retry. Else, like, it's a different kind of error and log it or whatever else.
Perhaps I wasn't clear. It needs to retry from the start of the transaction, not the statement I'm in.
Totally. And that, so if your statement, so say, just to put it very simply, let's say, this is kind of pseudocode now, to just make it easier. So say that that's in here, and you're doing more stuff up here and more stuff down here. So in this case, right, so say you've got your transaction and you're calling it from within the caller, then from wherever you're calling it, you can have it like immediately at the point of this error or whatever error is occurring in the middle, have it just return the error, and then in the original caller check it. So then you're just bringing it up a layer out. And so from that, then you can, and of course there's much more code to it than this, but of like, roll back that transaction and then recall this. And so yeah, does that make sense at all? Oh yeah. Okay.
I actually like your style where you use a separate if statement rather than including the command in the if statement. And I was wondering of your rationale for that.
Right. So yeah, actually in Go code you will see some people do this, and I am not a fan at all. But they usually only do it for if the function only returns an error. So like if you'll see this. And so if like the function only returns an error, then they'll just do it like that. I think that's just not readable, so that's significantly better. And of course, some people complain about like this if error doesn't equal nil being like littered throughout it, and I totally understand that complaint, but the benefits in my experience have been awesome because of that, as I mentioned, the explicit handling of the error conditions. And this idea, right, of like the error conditions for, initial connection to my database versus writing to this file versus like executing some random query, like how I handle those errors, I want to be different, and I also am able to think about that explicitly through just the error as the last argument being returned.
On the database copies, do you have any size restrictions like that in your environment when you're copying these databases?
Sorry, would you mind repeating the question?
The database sizes, do you have any restrictions on database sizes that they can request for DBO?
For DB? No, actually. So it's actually using PG restore under the hood.
So base backup.
Yeah. Yeah.
I'm sure if you addressed this before, but is there any concern with like TLS and like not being able to fire shard that basically?
Yes, sorry, that's a very good point. So if you are using PGNet Detective or doing what I was talking about in that, you need to turn off TLS.
So how do you do that then? Do you just don't use it internally because it's all in the same UPC anyway, or?
Right. So yeah,
Just disable it like completely from the app to the database.
yes.
Or share the private key with the receptor.
Yes, you can absolutely do that. In my firm, how I implemented it, I didn't. I just made it simpler, like just disable it. But yes, you could absolutely do that as well. Oh, sorry.
A random comment there, actually, libpq does have a big change compared to libpq and Go versus libpq and C has a big change in terms of behavior, that libpq and Go defaults to prefer, for SSL mode equals prefer, or require, not prefer, that's what it is, which means that you will have to explicitly disable SSL if you're in a non-SSL world.
Mm-hmm.
So just a heads up that you will bang into that.
Yes. No, totally. All right. Sweet. Give you guys some time back. Thank you.